container with most water. Learn the geometry, prove the pointer movement, and finish with an interview-ready dry run. Each number creates one wall. The index tells us where the wall stands and the value tells us its height. At index 0, build a wall of height 1. At index 1, build a wall of height 8. At index 2, build a wall of height 6. At index 3, build a wall of height 2. At index 4, build a wall of height 5. At index 5, build a wall of height 4. At index 6, build a wall of height 8. At index 7, build a wall of height 3. At index 8, build a wall of height 7. Walls 1 and 8 form the winning container. The blue region is the water held between them. Their width is 8 minus 1, which equals 7. The shorter wall gives a water height of 7. Now multiply width 7 by height 7. The area is 49. For this example, the maximum area is 49. Return the numeric area only, not the wall indices. The best choice is the wall at index 1 and the wall at index 8. First calculate the width. Right index 8 minus left index 1 equals 7. Next calculate the usable height. Water escapes over the shorter wall, so take the minimum of 8 and 7. That gives 7. Finally multiply width 7 by height 7. The result is 49, so the output is 49. A direct solution chooses a left wall, pairs it with every wall to its right, and repeats from every starting position. That produces roughly n-squared pairs. Each area calculation is constant time, but checking all pairs takes O of n-squared time. We need a rule that safely discards many pairs without calculating them individually. Place left at index 0 and right at index 8. This is the widest pair available, with width 8. Whenever either pointer moves inward, width decreases by at least 1. Width can never improve again, so after measuring this pair, which wall can we discard without missing a better answer? Assume the left wall is shorter. It limits the water height of the current container. If we keep that shorter left wall and move only the taller right wall inward, the width decreases while the height remains at most the same short left height. A smaller width multiplied by a height that cannot increase cannot produce a larger area. Therefore, every pair that keeps this shorter wall is safely discarded. Move the shorter wall. A new, taller wall is the only possibility that can offset the lost width. If both walls have equal height, either wall may move. Keeping either equal height wall gives a narrower container whose limiting height cannot exceed that same height. This implementation moves right when the heights are equal. Moving left would also preserve correctness. The important invariant is that at least one current limiting wall is discarded after every comparison. Compare index 0, whose wall has height 1, with index 8, whose wall has height 7. Calculate the width on screen. Right index 8 minus left index 0 equals 8. The shorter height is 1, so water can rise only to height 1. Now multiply the visible values. Width 8 times limiting height 1 equals current area 8. That beats the previous best of 0, so best becomes 8. The left wall is shorter at height 1. Discard it and move left inward. Compare index 1, whose wall has height 8, with index 8, whose wall has height 7. Calculate the width on screen. Right index 8 minus left index 1 equals 7. The shorter height is 7, so water can rise only to height 7. Now multiply the visible values. Width 7 times limiting height 7 equals current area 49. That beats the previous best of 8, so best becomes 49. The right wall is shorter at height 7. Discard it and move right inward. Compare index 1, whose wall has height 8, with index 7, whose wall has height 3. Calculate the width on screen. Right index 7 minus left index 1 equals 6. The shorter height is 3, so water can rise only to height 3. Now multiply the visible values. Width 6 times limiting height 3 equals current area 18. That does not beat the best area of 49, so the best pair stays unchanged. The right wall is shorter at height 3. Discard it and move right inward. Compare index 1, whose wall has height 8, with index 6, whose wall has height 8. Calculate the width on screen. Right index 6 minus left index 1 equals 5. The shorter height is 8, so water can rise only to height 8. Now multiply the visible values. Width 5 times limiting height 8 equals current area 40. That does not beat the best area of 49, so the best pair stays unchanged. The right wall is tied for the limiting height. Discard it and move right inward. The best area is already 49. Continue moving the shorter wall until the pointers meet. We still calculate every remaining candidate reached by the two-pointer rule. Pair 1 and 5 gives area 16. Pair 1 and 4 gives area 15. Pair 1 and 3 gives area 4. Pair 1 and 2 gives area 6. None exceeds 49. The pointers meet after the final comparison, so the maximum remains 49. The pointers have met, so every necessary candidate has been considered or safely eliminated. The best walls are at indices 1 and 8. Their width is 7, their limiting height is 7, and their area is 49. Return 49. Here is the concise interview explanation. Start with 2 pointers at the ends because that gives the maximum width. At each pair, area is right minus left multiplied by the smaller wall height. Move the shorter wall because keeping it gives a smaller width without any possible increase in limiting height. Continue until the pointers meet, while tracking the largest area. Across the whole scan, the pointers move inward at most n-1 times. Time is O of n, and extra space is O of 1. Place left at the first wall, right at the last wall, and initialize the best area to 0. Every iteration evaluates one container. Each pointer moves only inward, so the total number of iterations is linear. Multiply the pointer distance by the shorter wall. The shorter wall is the limiting water height. Move the shorter wall inward. If the heights tie, this code moves right. Either choice is correct because width shrinks while that tied height cannot improve. Return the largest area seen. The algorithm uses O of n time and O, 1, extra space.